要是感兴趣，可以发你一些 Salesforce 的文章，必须要去做。就是我不知道他们和我这个有没有结合。但你想 ，Salesforce 其实也是用 management 去 drive 一些东西，它有一些比较相搭。
那你不是做的什么？用它的设备去做实验。
大家还不关注之后的，大家现在只关注它做什么。
就是现在在干，就是怎么做的研究。
因为有两种方向嘛，一个就是 Salesforce 本身它为什么能够纠错，因为它有一定的拓扑结构，你就可以，它是一种拓扑方面，它就相当于我这个菜是一个非常好的资源，你怎么去利用这个资源去研究一些其他东西，比如说研究拓扑、研究相配，然后研究纠缠，各种各样的然后我现在做的就是结构差不多，都是那种垃圾结构，然后我用 management 去研究是整个菜，然后我把一个它是二维结构对吧，然后一层一层把它全测掉，全部都测掉，最后我剩一个边缘态，它边缘一般就是拓扑点所关心的地方，然后这个边缘态它是不是有一些非常奇怪的性质？它可能是一种其他的多体态，比如是一种强劲的多体态，像这种包括像楼下那个尤哈娜什么尤娜，他们做那个 management 有个 face transition 是类似的想法，就是我有一堆 Q 信息，然后我把它演化测量，我能不能看到它一些强面，然后测量和演化这是两个不同的拮抗的东西，测量之后把纠缠干掉，然后那个就是产生纠缠，大概就是结构都是一样的结构，只是大家怎么去不同视角去看。你好像计算的方式，就是我跟我只关注我不关注拓扑结构，我什么不关注，我就只关注技术性的东西，我会把噪声做低，然后用这个 Q 比特真正去编码去得到这个 Q 比特。然后像我们理论的人可能就更关注它这个结构本身有什么特征，能够产生一些什么样的纠缠态，对不对？我这边有两个工作，一个就是做纯理论的，就是我说的，就把全都用测量测掉，然后看它的边界态是什么样的性质。然后另外一个就是那个分析，我那个我没太参与，所以说。
那你在那边做的是用的什么？
我在那边第一个工作是纯理论，6年那个太难。
他们用的。
第二个是和浙大合作的，浙大是超导。
浙大有。
对，浙大应该是国内做的最好的超导。他们是专门为了做 Salesforce 去做晶片，他们能刻10，就是刻了100多Q 比特，结构就是我刚才说那个，就是为了做 Salesforce。他们目标就是对标谷歌，把谷歌干掉。
那100多个能做的多大？
就100多个 Q 比特。做的多大？
就是能做到一个芯片里。
对，就一个芯片里。那它100多个有可能是坏的，所以它可能做100个，然后能用的只有80个，大概是这样。
就是我看那些量子计算机不是都庞然大物吗？我的意思就是多大？
那个大东西是稀释这种机。
是什么？
稀释这种机，它和芯片一点关系都没有。芯片就指甲盖这么大。
那它不需要，就是它的Q比特不需要，就是额外的制备，就是做到芯片里头可以用。
他们一个 Q 比特就是一个约瑟分层点一个约瑟分层点其实就和我们现在的半导体工艺是一模一样，就是用刻出来的，只不过它要产生量子效应，就是量子就是超导，它用的是约瑟分点的超导效应。这个东西需要超低单位，所以它外边套一个特别大的稀释冷机。是这个原因。
就是那个东西是制冷的东西，然后其实它的 Q 比特就一点。
就昨天的人他的说法想法就是把那个，我感觉啊，就是想把那个
制冷机也放进芯片里。
对，就把那个机存起来，比如说我一通电，它自动给它制冷。我觉得他是说这个意思，你不然，就是你如果去过王先生实验室的，他们实验室中间摆的就是那么特别大的一个那个东西，只不过为了拍照好看，他们会把桶拆掉，里边就是一圈一根线，就是那个东西。但是不同平台不一样，但是。老板还来哇
？Guys, professor will be 15 minutes till.
Okay.
15 minutes.
15. Okay.
你看，这个就是我这个做的写的笔记，大概是看，这就是一个 CX code 的结构，这是另一个 CX code 的结构。然后呢，这些东西编码成一个logic QB，这些编码成一个logic QB。然后呢，我想对这个logic QB 采取一些态，把以后到零态上，然后就直接不看，就想通过一些东西把它把这个多体态传到这个多体态上。这是现在的一些想法，然后这个东西就是这打这样做，然后怎么去编码这个东西，结构就是这样子。我这4个例子，然后它和它是一样的结构，它和它是一样的结构，这是 S， 这是 Z， 这是 X， 就是这样子。然后方法就是1、2、3、4 Q 再加上一个 C 码，一个算 C 码，然后呢，通过这些门，把它全纠缠起来，对，然后就编码上，这很简单。然后你把所有操作都做完之后，这一个就被做好了。然后做好之后，比如说谷歌他们不做 teleportation， 他们就直接把这个态编码好，编码好之后就直接测点 Z 的。这一个 Z 叫一个 parity check。parity check 就只查这一个方框里面的4个 qubit 的，因为它们每下之间是连接性，把它拆掉，然后你有一个读出，一个读出。然后一个 D 的是3个 qubit， 你去算上这边也有一个 Z， 这边也有 Z， 就它只有2个 qubit 对吧？那你加上一个 Z， 就是你一共是有1、2、3、4、5、6、7、8个读出，你用这8个读出去 decode， 它相当于有一个密码去 decode 整一个它的信息长什么样，然后你的 decoder 会决定一些效率，这些 decoder 能不能正确的识别哪个 qubit 发现错误，这是另一个东西。就是我这个 CX code 它有一个理论上的纠错上限，就 CX code 比如说我支持造成10%以下我都可以纠错出来，但是你的 decoder 不一定能做到，就是我理论上能做的编码，我的 decoder可以有我的 decoder。decoder 如果效率不高的话，其实和计算机一样，你代码写的不好的话，你其实用不了它全部性。然后呢，这样的话就产生2拨人制作，就昨天的人物的问题。我硬件就把这个芯片让你做的尽可能的好，这是硬件上。那软件上的挑战就是我怎么样去处理这些数据，因为比如说我之后做非常多的 qubit 的话，那我整个的数据是非常庞大，是2D 次方的所有的信息，我怎么样快速的把这个东西 decode 出来？昨天他说的，你需要超换，然后有些人说那个超换的你是不是需要太多了？他说你不要认为算力是优势，不多点，说他意思就是我用超换很正常一件事情，但数据大了之后我就不可能，就很难去用我现在去搞了。他的意思就是你可以结合人工智能，人去做，所以说这整个就是一个巨大的大投资的一个池子，也可以讲各种各样的故事，比方这个。这是一个编码方式，这是我说的一个 check 上面，然后这就是那种 CX code， 在 CX code 的背景，那些下面是吧？目标就是创造 P 小于，就是我每个 qubit 造成的小于然后我实验上把这些描出来，我就论证出来我做出来的一个就是这样。对，就是这样。对，然后你看，你随着 D 的增加，你这个理论这个叫什么？它这个 error 是在持续减小，然后在下面在这个 threshold 或者以上，它会持续增加，就是这个下面2D相对，看着 然后谷歌是做到了第5期，现在全是理论，谷歌做到这儿。我这全都是理论，全都是数据，这东西是没办法理论解的，就只能数据。后面我就不知道，我走着过堂课。我觉得坑太大了，咱就不能碰，各种别碰。
就是了解一下它这个量子结构现状。
是，就比较前沿。咱们组，对，你看，就你知道我这张图，刚才是上面那张图是那个点图，知道在都是在超算上跑，就跑那张图花费就是超算，什么沈周一号，你听过吗？
就是
超级量子计算机，
量子计算机。
不是经典计算机。
经典计算机，但是它算是比较。
你看我们这一个是一个 CPU 对吧？超算是就几万 CPU 绑一块，就纯算，然后跑一次可能需要一个超算，日夜不停的跑1个月，然后花好几千块钱才能跑一张图出来。
图就是那个数值的。
对，花费非常大，代码都写的巨长，有时候可能上万行代码，特别烦，受不了了，该做啥？
那你们当时是个人做吗？还是有什么合作？
我刚才给你看那个项目，理论是我们做的，和实验室啊，然后再往前，我之前那个项目就纯自己做，数值其实就可以纯自己做，就是理论和数值没有吧？
那你之前不是说你当这个老板只有你一个学生，就是你们2个人？
对，是的。
因为我感觉像这种的话，可能需要比较大的合作。
其实就依靠一个人，因为你代码太复杂了，你2个人也看不懂，就只能一个人全看。每次敲回车都非常压力非常大，一个回车几千块钱没了。
一般合作的话，可能会写就注释，会写很多注释那种。
这个也得写很多注释，因为很多代码
自己
也忘了太多了，太多了。我觉得我在那半天里写了10万行代码。哎，他们不用拍的，拍的摄像太慢了。
就没有什么
处理。这个。
我好像听说过这个。
就他不是年轻，他才10几年，就是他语法拍的差不多，但好写，但是速度和 C 是一样的。
为
啥？就写的好。我也不知道为啥就写的好。用 Python 本质上是无法编译的，组2个编译其实不难，因为 C 太古老了，你只需要把 C 的语法改变就是这样。
Python 就是相当于他把很多包就是他直接给你，所以写的这个文艺。
对。
C 的话就很多底层函数得自己写。
对。那你也不能说我们这么简单，你看我说的这些东西基本上全是解析的，而且全都是数值，它没办法解析。那我们是纯解析。你问我什么？你问我哪个 FN 我都能算，这是非常厉害的。
但是我感觉它就是太狭窄了，可能只能适用于这个。
对。
其他的不能。
我们这个严格上说是开放量子系统中的一个非常具体的分支。
比较具体。
对，你像开放量子系统，它是用林姆大的方式去表述这个脑硬核的过程。那我们直接就是强测量，把它全干掉，都不是那么弱监测，林姆大的方式都用不到。
昨天那个博士后问我，他说他们用林德布拉的方程，说你们是不是用的比林德布拉的方程更复杂一些？他还复杂，因为他觉得林德布拉的方程很简单，然后我说其实比林德布拉的方程还要简单。
我们说简单，完全用不到，不需要。他们做的更真了。但是我们这个也有。
但他们是理论。
对，所以说更真了。但其实我们这可能有更多的一些应用。比如说，我最近一直在想，比如说你把它放在多题里面，你英语这个文章，因为何朝王录的文章你看过？
我没看。
他就是用我们这套方法，大概思路就是把这个系统往大 C 的侧面去管理，你把大 C 设计好，它是一个多体态，你能用它去制备一些很复杂的多体态，就纯靠测量，做这些多体态。就是我觉得它在多体里面肯定有很多应用，但是因为还是不懂的问题，所以说进度比较缓。
是其实也只是无做声的情况下有一个
对，
有做声还是
他们也不关注这个，也不关注噪声，有噪声的话就只做学生，一点理论都没有。我之前那篇文章就是，我们也关注噪声，大部分情况他们做的非常好，差一点噪声，咔一下就没有，他一点突破口都没有。
你看这个就是我应该给你看过这个图，就是昨天你说的 TT 和 TR，这个我感觉这个算蛮好的。
这是 TR，
这 TR 这应该它比较大，这 TR 就是以前是有200个 T 是200个
TR 就是一次实验过程当中的。
对，但是我这个 TP 就是因为我的目标，我之前的目标是测到无穷次，无穷次你就没有办法在量子学计算机上测。
就是你的 TT 其实是我们之前文章里的 TR， 然后你这里的 TR 有个 TT 能一块儿。
我觉得不是，就是实验上的 TR， 但是不是理论的 TR。就是实验上就是测这么多次，25次，但是理论上这个测量并没有结束。
是你实验上的测量数值 TT， 理论上是这样。
这个再往下还可以测到，可以获得无穷次的结论，但是这里我就展现它从 TR 小的数字。如果你看1000、500次是这样的，然后1500，就是现在IBM能测1000次，然后但是如果1000次的话，它是没法收敛的，大概就这样的一个，它没有办法测到这个。
哎，那你测量一个是0，一个是1，是吧？
这不是0，这0是1。
这是0到0，这是1到1。
对，0就不会有。
收敛了吗？
收敛。
收敛。
实
验上看到有收敛。
这就是实验，这个是。
它的 translation 不会消失。
不会消失，就是模型上。
你实验上看的对。
对。
好奇怪。
这个理论也是这样。
多大的 P 这是
？P 大概10的负。
百分之几？你别把它写的太不正经。大概什么量级？
反正就是10的负3次。
这么小吗？
这个是。这个2笔特别小，2笔我记得。
这小。
这个因为0到1嘛。expectation。
那这挺 make sense， 大概是1%的这样。
然后其实这里的话就是这个是理论，然后这个是我也不知道这是同一个。
为什么把它画在一块？
因为不然都合在一起。
这个画成点了，这个好写。
也可以，但我加了门槛。
不用门槛了。
而且还有一个原因是，这个 peak 和这个 peak 的值差有点大，如果画在一个图里的话，这个差别有点明显。
是1，这是1。
不是啊，这个是10的负3，这个是4000，这个是2万，差的有点大。然后我后面也解释了为什么它差的有点大，但是画在一张图上的话就显得格外大。但是它就是一个2个 non-degenerate measure， 就是全测，就是有点就是简单这些。
help? Need help?
Can you plug that under the table?
Yes.
Just to see, right?
From here?
Yeah, any place on the table.
我还觉得我做这个有没有，就是这种噪声的研究有没有用？因为大家都在想办法减少噪声，但我就去研究。什么叫手动调节？P 是啥？就是噪声的。
你把这个皮看一个轴，这个可能它的看你这个片了，或者闹完之后的，你看还有一些随着尺度的按有一些，
是啊。
或者是其他的，一些皮人家肯定有一些变，然后有一些同样的像这样这个，这个是那样子，关注我自己的屁股，我那个小，因为你的手后，你觉得以后比较的话，甚至这个头比较小。我是一个人，对，关注。
我这个的结论就是目标就是说明小噪声会有一个很大的影响。
我刚才是觉得，你其实在告诉他，这个类似于极限，这种不同的丧失一些，一千个，能达到正面一个比赛，或者说这个是非常好。
So already recording. Okay. Good. We can have this screen also. Yes. Hey everyone. Okay, so we'll go today into really fascinating theory to describe this scattering media. I mean, it's really fascinating. You see, the ideas are very simple. Okay, we derive the equation really with the ends, and we get very powerful tool. Okay, so today I will try to introduce you to the method of transport theory. So I would like to derive today the radiative transfer equation, which is really the basis to describe multiple scattering in disordered media. So this is a fundamental tool that we are going to establish today. You see it was introduced actually in astrophysics first to describe the propagation of radiation from stars, from planets, between stars. It was also developed in the field of neutrons, neutronics, so neutrons in a reactor, in reactors, yes. I will introduce several quantities, several photometric quantities that will be used in this chapter. And you'll see this is really a phenomenological approach of this physics that we are going to establish today. Okay, so you are with me? Okay. So let me start with the general introduction. What I want to say here, single scattering approximation, that was really the starting point for us in the previous courses. Starting from single scattering, we did some approximation to be able to solve multiple scattering. Okay, one of them was, if you remember, the Born approximation, considering dilute samples. Okay, so scatterers far enough so they don't contribute. They only contribute through the scattering of the incident light. That was really the starting point, very basic approach that was good for dilute sample, for almost quasi-transparent samples. Not valid when particle density is large, okay? And you remember that the ballistic light becomes comparable or less than the incoherent intensity. These two terms, one was the ballistic component that decays as you propagate through the scattering medium, and instead of, this is replaced actually by scattered light, diffuse light actually, that we're going to explore in the following courses. So you remember we defined the mean free path there, and when the mean free path is on the order of the size of the system, then you start to be careful, and this approximation is not valid anymore. And the multiple scattering becomes dominant in this system. Okay, so you cannot neglect the fact that the light can be scattered by one scatterer and go to another one, and okay, so you have many contributions due to the scattered light in this system. Okay, so we have two distinct approaches. One we developed last time, which is the analytical theory. I will just show you one slide to review that rapidly. And the one that we are going to talk today about is the transport theory. So one is almost, I would say, rigorous, based on some approximation, but it's a mathematical approach. The other one is more heuristic, based on simple concepts. Okay, so you remember from the last chapter, chapter 5, I introduced you using the green formulation. I introduced you to the statistical approach. Okay, statistical means we do ensemble average. We average over many configurations of the disorder system, and then you can write some equation on the average of the field. That's the Dyson equation. Average on the square of the field, of the intensity. So that's the Petz-Salpeter equation. There are different methods, like the diagrammatic method. I didn't go very far into that. Okay, so that was really the mathematical approach. And I use a phenomenological approach to describe, actually, to define the mean free path, which is the Beer-Lambert law, which tells you that you have an exponential decay of the ballistic light, so the photon that goes straight, as they progress inside the system, they get scattered out. Okay, so the light that goes directly through decays through the sample, and the Beer-Lambert law, so this exponential decay, is on the characteristic length scale, which is the mean free path. So we define the mean free path, the scattering mean free path, the transport mean free path, if you remember, and we review the different regime of propagation. So that was last week. That's a quick review. Okay. So today, let's start with the transport theory. Okay, where we are going to describe how electromagnetic radiation propagates through strongly scattering media, that can not only scatter, they can absorb, they can also emit if you have sources inside the system or if you have gain. Okay, so it's a very general approach. Scattering, absorption, emission, and that will give us a kind of framework to describe the radiation that propagates through such a medium. So that's the first objective. Find a theory to model the propagation of electromagnetic radiation in an absorbing or emitting or scattering medium. Okay. So this theory was initiated by Chandrasekhar. So he wrote actually a seminal paper on the actually book on the transport theories, radiative transfer theory. So he's really the pioneer in this field. Not only he developed the theory, but he also proposed solution for the equation. So he studied the equation and solved the equation for specific cases. So he brought some exact solution that have been used a lot in astrophysics, for instance. Okay. What is interesting is that this approach is equivalent to the Maxwell-Boltzmann equation. So maybe you are familiar with that equation. So that's an equation for particles that collide in a gas, for instance. Okay. So you know maybe the kinetic theory of gas. Are you familiar with that? I guess you got some class on that, but you didn't like it. Yes. Yes. Okay, Maxwell-Boltzmann equation. So this is a description of just particle that bounce in some volume with collisions, and when you, depending on the pressure, so the density of particles. Yeah, you introduce the temperature there. Okay. So very similar to that approach, and also very similar to neutron transport theory, which is used to describe neutron collision in neutron elastic collision to describe how do you call that? When you want to describe, let's say, what do you say? Yeah, fission. I was looking for the fission of atoms. Okay. So you have actually a neutron that hits a big atom, radiative atom, breaks it in pieces, and there is a chain reaction that leads to fission of the matter. Okay, so this actually is described in the same way for us as photon colliding on scatterers inside the scattering medium. Okay, so they are very close approach and very similar. Okay. So let's see where I am here. Yes. Okay. So transport. So application for this approach. So yes. So related to astrophysics, you can actually explore the stellar atmospheres or the planets' atmospheres by measuring absorption. So you see the rays in absorption, emission spectra. So that's really based on this approach. Also on Earth. Okay, so that's related to climate. You want to actually find the balance between the light that is shined by the sun on the ground or the atmosphere of the Earth, and what is re-emitted by the Earth itself. So there is a radiation budget that you can calculate, and is related to climate and provision and measurement of elements on the Earth atmosphere. More close to what we are doing, penetration depth of light in scattering media. You want to image through scattering media, so you want to be able to penetrate the system and to get information about the scattering media, like tissues, biological tissues, yeah, something, yeah, photon transport in optical imaging system. So can you actually use the diffuse light to image something inside the body, for instance, okay, a tumor or something like that, okay? If you use the ballistic light, you know that this ballistic light is going to decay very fast, so you cannot go very deep to image inside the body, okay? But the diffuse light goes quite far inside the body. Can we image what is the resolution that we can achieve in these imaging techniques? Okay. I mentioned application here to atmosphere and underwater visibility. You can look at this movie that explain how you use this so-called Secchi or Secchi disc. Okay, you drop this disc, actually, that's a method that is used. They drop the disc, so it is attached to a long string with markers every meter, and they drop it, and as soon as you don't see anymore the disc, that means that you reach actually the distance corresponding to the transport in free path, okay, because you don't see it anymore, you don't see the source anymore. Okay, you can measure that, and that gives you information about the turbidity of the water, the pollution of the water, okay. Okay, so all this is based on the formulation of the radiative transfer theory, so marine biology, optics of papers also. Yes, papers are white paper, but they can be characterized by the scattering. Okay. So actually there is a field in this domain. Okay. Propagation of energy in atmosphere of planets. I said it before. Okay. The red spot of Jupiter, for instance. Okay. So actually this theory is very flexible and capable to treat a large range of phenomena. What I want to say here is that this theory covers most of the regime of propagation. If you remember the Eiffel Tower, okay? So unless you are in a regime where the scattering is very, very strong, and you cannot neglect actually a certain number of things that I'm going to describe now, this is really very, very efficient, very flexible, very useful in many, many domains, okay? So that's what I want to present this approach here. Okay, so transport theory. So this is an abbreviation. I mean by that radiative transfer equation. Okay. And I had an abbreviation, but we'll keep this is the only one. Radiative transfer equation. Okay, there's a fundamental differential equation that we're going to derive to find, demonstrate. So it's not rigorous, so there are a number of hypotheses here. So it's a transport equation on what is called the specific intensity. I will define that, okay? So we are not talking about photons anymore here. We are going to consider some kind of more macroscopic quantities. The wave nature of light is being ignored in that case, okay? So we don't take into account interferences. We are not considering the field, we are considering intensities only, okay? So if the wave nature of light is ignored, that means that it's like particles actually propagating in a medium. For simplicity, we also ignore polarization of light. We assume that polarization is randomized in the system, so there is no polarization. The polarization does not play any role here. I skipped that one. So diffraction and interference effect only included in the description of single particle scattering. Okay, so at the microscopic scale, at the scale of the scatterer, okay, we can use what we learned at the beginning of this course. Okay, how to calculate the scattering diagram. So that's at that level, but at a microscopic, at a larger scale, we will ignore completely the interference effect. Okay, so between scatterers. So how do we compare the theory that we are going to describe today with last week's theory, the analytical theory? So they describe the same phenomenon, okay? but there are different starting points. The radiative transfer equation theory is more like a particle-like transport. Okay, you consider like particles, not waves. Okay, so if you remember in the diagrammatic description with the expansion with diagrams, we consider only the ladder diagrams, considering only intensities. Okay. On the other hand, the other theory is a wave transport theory. Okay. So you include also interferences. You include correlation in the field. Okay, all this is very important in the full theory. Okay. Okay, that's something that I will not address. What is really the relation between the two? That's quite involved, quite complicated to understand. Okay, but just to remember here at the end of the story. Okay, if you want to be complete, the transport theory must contain information about the correlation of the field. Okay, at the end of the story, you need to include correlation, phase, interferences. Okay, and that will be the end of this course. I will address this question. Okay, good. So let's see the outline of today's course. First, I'm going to define several quantities here, photometric quantities. Okay, we'll see. Then we'll proceed with writing the balance of energy. So the energy flux evolution means how the energy is propagating inside the system, lost, absorbed, scattered, or amplified in the system. Okay, and at the end of that, we will be able to write the radiative transfer equation. Okay, and we'll test this equation to see what is the ballistic part, what is the diffusive part of this equation, how they contribute there. Okay, and we'll see how naturally from this equation comes actually the length scale that we learned about last week, essentially what we call the transport mean-free path. So when you use this transport theory, this comes naturally actually from the equation. Okay. So before starting, a reference. This is Ishimaru. Okay, that's a textbook on the field that everyone uses. So if you are interested, you can go deeper by looking at this book. That's really the basis of my course here. Okay, any question? That was really a general introduction just to motivate my interest for this theory. So let's start. For the photometric quantities, okay? So we want to measure some quantity based on the light intensity. Okay, by the way, I just today put pictures of the Golden Gate in very nice situation with the clouds, and that's beautiful pictures. Okay, so just a small reminder about solid angle. Are you familiar with solid angles? Yes. How to define that? Yeah. If you want a solid angle in 3 dimensions, is the equivalent of an angle in 2 dimensions. Okay. To make it very simple. Okay. So in geometry, a solid angle, symbol omega, is a measure of the amount of the field of view from some particular point that a given object covers. So you look at some object. I'm looking at the screen from my position. Okay, so it covers a given solid angle. Okay, so I measure how large the object appears to my eyes as an observer. Okay, looking from the point where am I. So this is simply the surface. Okay, divided by r squared, where r is the distance from me to the screen. Okay. Okay, that's standard. That's okay. No, that's new for you. No, actually, no, you know about that. Okay. So if you want to, if you consider the spherical coordinates are r, theta, and phi. Okay, so the volume element is r squared sine theta d theta d theta d phi. So the elementary solid angle is d omega. So d square s over r squared. So this is simply sine theta d theta d phi. Okay, the small surface here divided by r squared. Okay. So you understand that it depends on the distance where you are. Okay, if the object is very far, you will see it very small. Okay, and the solid angle is quite small. Okay, when you get closer to it, then it gets the solid angle increases. Okay, just because it's divided by r squared. Okay, and it's proportional to the surface. Okay, so that's easy. So basic properties of optical radiation. So look at this statement here. All sources occupy a finite solid angle. Okay, so you have a source. Okay, it emits. I mean, it's not like a point. It's not a point source. Okay, it has some surface. Okay, so if you look at it, if you look at this source, it appears in a given solid angle. Okay. So as I wrote it here, there is no such thing as a true point source. Okay. So for instance, if you look at the sun, okay, you can measure from the position from Earth what is the solid angle for the sun. Okay, so it occupies a solid angle of 6.5 10 to minus 5 steradian. So steradian, that's the unit for solid angles. Okay. By the way, what is interesting is that you know that the moon is about 400 times smaller than the sun, okay? But it is actually
much larger solid angle, no?
No, actually, so it's much smaller, 400, okay? 400 times smaller.
The solid angle is larger.
No, but its position closer to the Earth by the same amount, okay? So actually, the solid angle between the moon and the sun is about the same.
Oh.
That's why we have eclipses. Okay, an eclipse is, you see that the size of the moon is exactly covering the sun. So this is just by magic. Okay.
It's 400 times smaller than the sun, but 400 times closer.
Yeah, right. So yeah, so it's not 400 times because it's r squared. Okay.
Yeah.
So actually, it's the square root of that. So you have to be careful. Okay.
Square root.
Okay, so actually they have exactly the same angular diameter. Okay. Okay, so that was just an example to tell you that just a source as a solid angle, typical solid angle. So that I don't know what I meant by that. Forget that. We need to combine these properties, intensity, size, direction, to obtain a general quantity that requires a source of light. Okay, let's see. So let me define the main quantity in the field. It's called the specific intensity. Okay. So what is the specific intensity? So if we first define the radiative power dP of omega here, crossing an elementary surface ds, so you have the surface here, okay? So imagine you have a small hole, okay, like this surface ds, okay? Light's coming through this hole, cross this hole, and you look in a given direction, okay? So you look at the radiative power, I mean the elementary radiative power dP of omega crossing an elementary surface ds, centered at some position r, with some normal direction n. So you are looking in an elementary solid angle d omega centered around the direction u, okay? And all this is in a frequency range between omega and omega plus d omega, okay? So you can write this radiative power as a quantity here times ds d omega and this small omega, sorry.
Quantity of what?
Wait, I'm going to tell you that. Okay. Times u times n. Why? Because you see the normal of the surface n, okay, and the direction of observation u. Okay, so you see that if you look at your opening here, if there is an angle, you reduce the opening. Okay, so actually that's just a cosine theta. Okay, so it depends on the position and on the angle between the two directions. Okay, so that's un times ds, that the omega, that this, so the omega, the elementary solid angle, and this small omega, the elementary frequency range. Okay.
What?
So this term here, just by definition, this is the density of power. Okay. That's the density of power because its unit is by surface, by solid angle, by frequency. Okay. So this quantity I understand. Okay, I can understand what is the relative power, and I define the specific intensity as the density, the power density through this small angle. Okay, so L of omega is the power density. So this is the power per elementary surface ds, centered at r, per elementary solid angle d omega in the direction u, and per elementary frequency range omega, omega plus d omega. Okay, around omega. Of what? Of a radiation starting from r and received or emitted in the direction u. Okay.
Can you tell again what's the difference between ds and the omega?
ds and the omega.
Why we need both of them?
No, so ds, that's the small aperture you are looking through. Okay. Okay, so the light. Imagine you are looking at.
The radiative power through this.
Through
this
small
region.
hole. Okay, this small. I'm looking at the light of the projector here.
It's
So
the
the light that
ds
goes
of the
through-
hole, no? It's the ds of the hole itself.
Yeah, that's the surface
Yes,
of the hole. If you
and the omega and the other one are the angles. of-
omega, so that's I'm looking in. So to my eyes, so I'm looking here, like the sun. I'm looking at the solid angle given by my surface here. Okay, and this one is just because we have a broad spectrum. Okay, so we want to look at different frequencies, elementary frequency range d omega. Okay.
So the omega, it depends on the point of view you are looking.
Yes, it depends on you, the
Yes.
direction of observation. Okay.
The observation. Yes.
Okay. Okay, so I just put this picture here for this term UN here. Okay. You know the difference between the sun and in summer and in winter. Okay, so you see that.
So this is the ds, the large area.
No, if you take the same ds here, okay, you see that the power radiated for this ds, okay, is smaller than in winter than in summer, okay, so you get less heat in winter than in summer.
So the angle of the
Because you know
Karna
that
Shemesh,
yes, the sun in winter is really down.
the direction of the sunrise is the d omega.
Right, that would be the d omega, right? Okay, so that's
What?
the u.
The ds in the winter is much bigger. The ds in the winter is much bigger.
No, but
No,
the d.
No,
d omega.
No, before
It's the angle, the u, the difference between u and the normal to the Earth is different in winter. It's much
larger in the summer. Yes,
In
I thought.
summer the sun goes.
Yes, that's right. I thought you were talking about the ds of the shape here.
No, the S is your head, for instance.
Yes.
Okay.
Okay.
So how much heat you get on your head in winter and
And the angle of the sunrise is the d omega.
right.
Okay.
Okay, so that's an illustration of that. Okay, so you can feel what is the radiative power, and the definition of the specific intensity is just a density of this power. Density per unit surface, per unit omega, per unit solid angle. Okay. There are different names actually for it. It's called the specific intensity. It's called also the luminance, the radiance, the brightness. I mean, you can find these different terms, these different names. They are equivalent. for people that are familiar with photography. Photographers, yeah, that's the typical word that are used. Units, so this is watt per meter square per steradian per hertz. Okay. So let's try to understand better how we can measure the specific intensity, this L of omega. Okay. Because this is a specific quantity in photometry. So just consider a detector, okay, like this photo detector here. So to measure the specific intensity from a source, take a detector with a small receiving area, okay. So it's another way to look at it. You take a detector with some area, ds, delta s, okay, and solid angle delta omega, so depending on the position of your detector relative to the source, okay. You can use a filter to select the frequency range delta omega around omega, okay, and point it in the direction minus u, okay, so reverse, okay. The specific intensity is the total received power, and it's density, so divided by delta s by delta omega and delta small omega, okay. So it's a reverse way to look at it. You put the detector, so the source is here, and okay. Any question?
This is how sunglasses works?
Why?
Like
No,
with
they are bipolar, no?
the bipolar and the angles, and they control the power of the light through the sunglass. Okay.
No, I mean you can use either an absorber or use polarization, and then you have to put something in the middle. Here for now we are just looking at light propagating in free space, okay?
Okay.
And we just define this quantity, okay?
Mm-hmm.
So this is just really the building block of all the rest after that, okay?
No.
So interesting case. Okay, I think that's quite interesting. And then we can make a break if you want. The case of what is called a Lambertian radiation. So if so that's the definition of the radiative power. Okay. Maybe you can take a piece of paper on your computer and write there will be like four definitions. Okay, so that's the first definition. So the specific intensity. I get lost also at some point. So that's the specific intensity. That's the radiative power. Okay, elementary radiative power. So that's the definition of it. Let's see the case of isotropic radiation if L is constant. Okay, so the density is equal to, let's say, 1, okay? Whatever R, U, I put T here, so the time. We didn't discuss time, but that's just, but it's not very useful here, there's no time, okay?
Why the U dot, the normal, comes to only cosine theta?
Well, so this is the product here. This is the UN is cosine theta.
Yeah, but it should become UN cosine theta. There's
No,
only cosine theta.
U times N, this is what I call cosine theta here. This is the dot product between the two vectors.
Yeah.
It's cos theta. Okay? So I just replaced UN by cos theta. That's a scalar here, okay?
Mm.
And that tells you actually this effect here, depending on the orientation of your surface, okay? But that's very important, okay? So L can be a constant, okay? Can be 1, okay? So the density, that means that the system, the medium that, or the source or whatever, okay, emit a density of power equal in any direction, okay? All direction, if you want all frequencies, okay? So that's the case of isotropic. So if you take an isotropic radiation, okay, with a specific intensity which is constant, okay, then P here So you can just remove that. So you can integrate P here. So actually you don't have to that. Yeah. So P is just P0 cosine theta. Okay. So that's the distribution actually of radiative power by a source or by a reflector, for instance. Okay. In that case, this is called a Lambertian source. Okay, that means that it's a source that gives you a distribution like that. Okay, cosine theta. Okay, so you have, let's say, for instance, you have a surface. Okay, this surface just reflect or diffuse the light that is incident. Okay, you have light incident on the surface here. Okay. If this is a mirror, okay, you get only the specular reflection, okay? If you have a mirror, you get just the Snell law, okay, you get a reflection.
If there is what?
If this is a mirror, like a metallic mirror.
Ah, mirror, okay.
Okay.
Mm-hmm.
Okay, so you get exactly the reflection.
Mm-hmm.
But if you scratch the mirror, okay,
Yes,
or if you put like some white,
scattering.
you put some paint, for instance, the paint of the wall, okay?
Yes.
Light will be scattered in all direction.
Mm-hmm.
Part will be specularly reflected, but the rest will be reflected
Diffuse
in all direction. Okay. So if the radiation, if this function is 1, is constant, if the scattering is isotropic, that means that you don't have any more specular reflection. Everything is scattered, but you see that because of the cosine theta, most of the light is reflected vertically like that, okay, and the rest you see decreases with the angle, okay. You don't have a lot of light that is scattered
Yes.
parallel to the surface here, okay. That's the cosine theta function, okay. So to illustrate that, for instance, I know you don't see it very well here, but you can see it here. So you see 3 types of surfaces here. So this one has still a specular reflection. So there is a source somewhere, okay, some projector of light. So you see the specular reflection here, and part is diffused, okay, scattered, okay. Still here there is some trace of the specular reflection, but if you have a perfectly Lambertian surface, okay, that means that it's an isotropic. The scattering is purely isotropic. Then you have a nice diffuse light coming from the object. Okay. Equal luminance, equal specific intensity or luminance when viewed from all directions. So this is called a Lambertian reflection. So this is very interesting. Actually, I illustrate that because I think it's very useful actually. So this is what you use when you do photography. Okay. You try to have diffuse lights, okay? You don't want this type of picture. This is terrible, okay? Why? Because you have specular light more than diffuse light, okay? So you want a source which has a nicely diffused light with the Lambertian profile, okay? And then you get a picture with the lightning which is much uniform, much better, okay? You see another example here, okay? So you can actually adjust the lighting in this office, so you don't have this kind of direct light, but you have a nice diffuse light in the room. Okay. So that's what they call Lambertian light sources. Okay. Maybe 2 minutes. I define the 2 next quantities. So from the specific intensity, okay, let's do that after. Let's make a break. I go over that after that. Yeah. So it's not too much at the same time. Okay.
Okay.
So let's break. Any question?
15 minutes. 15 minutes.
That's a lot.
So okay. So 10
Well, 10
minutes.
minutes. Okay.
Okay, 10 minutes. No problem.
We can round it up.
哎，我不知道聊什么。
是我打的，赶紧写。因为他好好的电脑，好好的因为要从开始。我来听你把一节工作的路，然后赶紧写。
你要去干嘛？
我就问他一件很小的事。
Regarding that program you said you send me to find the correlation.
Yes.
I actually used the equations that we discussed last time,
Okay.
but I'm not getting it as one. I'm getting it more than one, and it's not close to one also. Like I'm getting very high, very large values. So if I'm using I minus I mean in the denominator, I'm getting very large values. If I don't use, I will be getting some reasonable. So I wanted to discuss regarding that.
Okay. I want to show that. I don't I forgot to look at that.
The switch. And the tube with this slit, we cleaned and it's ready for exposure.
Okay.
So we are waiting for okay. You can have a look at it when we do.
want me to call the other guys?
Yes, okay.
Okay.
Shabam is the one.
So two quantities I'm going to define from the specific intensity of luminance, okay, L omega. The first one is the radiative flux vector, okay, Q. So you see this is the integral of over all direction U, okay, weighted by the value of L in that direction. Okay, you are with me? Yes?
This is the flux through the omega?
Yeah, so you integrate over all the directions, you integrate U, so the direction itself, weighted by L of omega, okay? So it's easy to see that, for instance, if L of omega, L omega is constant, okay, so if we have a uniform scattering of the light in all directions, okay? So if this is constant, you take it out, what do you find?
The flux.
What will be Q? If L is constant, integral of
If
U.
L is constant, what is Q?
Integral of U, the omega. It's you see, U is a vector, right?
Yeah.
So if you have a vector in that direction and in that direction, they cancel. Okay. If you sum in all directions, this will be 0.
You say if L is constant.
So if L is constant, if you can take it out of the integral, then you have integral of U the omega, and integral of U the omega is just 0.
0.
Okay, so if you have a isotropic emission of your source or your scattering medium, okay, in all directions, you see that Q equals 0, okay? But if it's not equal to 0, that it means that it has some direction, okay? It gives you like a flux, like a direction of radiation, okay? So this is very close to, very like the Poynting vector for electromagnetism, okay? So that tells you actually the privileged direction. If there is a direction of radiation, so that gives you the flux in that particular direction. Okay. So that will be used at the very end of this course. Okay. Integrating Q over a surface S gives a total radiative flux which crosses this surface. Okay. It's a vector, right? This is a vector. That's the first quantity, radiative flux vector. And the other quantity that we can define is called the energy density. So this is by integrating, so there is no more U here, by integrating L over all 4 pi steradian, okay, you get what is called the spectral energy density at position R time t if you introduce the time, okay. C is the speed of light. So where this comes from? The energy density U of omega can be related to the photon volume density per frequency unit. Okay, so if you want to count the number of photons radiated by your source, okay, so that's the number is n. So U is just n times h bar omega. So that's the density of energy. Okay. I just want to show you. Okay, if the luminance is isotropic, then you have a simple expression for U. Just to show you, it's not a demonstration, it's just an illustration of where it comes from. So we want to define an energy density. Okay, energy density means energy per unit volume. Okay. What is energy? Energy is power times time. Okay, or dt in that case. So if we have, so you remember this surface, if we have a beam that enters this hole and radiates out of the hole of the surface, okay, at speed c, okay, it will fill a cylindrical volume of area ds or dA with height, so it's like a cylinder with height c dt, c times dt, so that's the length of the cylinder after time dt, okay. So that's the volume. The volume is dA, the surface, times c dt. That's the volume of the cylinder. So the energy density is the energy, power times dt, divided by the volume, okay, dA times c dt. Okay, I simplify by dt, so it's power over dA times c. And you recognize here that power per unit surface, this is the density of power, okay, so that's exactly the specific intensity L of omega, okay.
This is new for us.
No, this is the definition that I gave at the very beginning, so that the specific intensity L, okay, it's a density of power, so it's the power per unit surface,
Okay.
per unit angle, solid angle, per unit frequency, okay. So here you recover here the specific intensity, okay. So you see, so at the end of the story, you get this expression. You understand where is the 1 over c coming from here, okay. So actually, the 1 over c allows you to convert from the specific intensity, so a power, a radiated power, into an energy density, okay. That's what I wrote here. Dividing by c converts directional power flux into energy per unit volume, and integrating over all solid angles includes radiation from every direction. Okay. So that just to summarize. Okay. So you can keep this page somewhere. Okay. We have 4 quantities that have been defined: the specific intensity. Okay. Called also the radiance, brightness, or luminance. Okay. With this picture over there. Okay, so from there the radiative power is the specific intensity, so the power density multiplied by ds d omega and this small omega, and also multiplied by cosine the cosine theta, the direction relative to the surface, normal to the surface. The radiative flux vector is the integral of L times u d omega. Okay. And the energy volume is simply the integral of L d omega with 1 over c in front of it, okay? Which is the number of photons times h bar omega. Okay, so that summarizes this chapter, okay? Not more than that, okay? So now we can start to do something with these quantities, okay? Essentially, this quantity will serve us, and at the end, I will use this flux vector here. Okay, so second part of this class. Okay, we describe now. I want to describe now the evolution of the what is called the directional energy flux. Simply, what I mean by this expression, energy flux evolution here, this is simply the balance law. We are going to write a balance law that tells you how much energy changes in time due to transport through a scattering medium or a given medium, not scattering only, you can absorb, you can do it. Okay? So we are going just to do a budget of energy, okay, the balance of radiative energy when scattered through some medium, some given medium. Okay? Until now we were just defining quantities in open space, in free space. Okay? Now let's go through a scattering medium, or through a medium, not only scattering. Okay, so we are going to describe phenomenologically this flux evolution in the medium. Okay, so important to understand what we are looking at. Okay, we are looking at the medium made of small particles, small scatterers. Okay, we are not looking at that scale, at the microscopic scale. Okay, we are looking at a larger scale. Okay, where we are going to define parameters like scattering coefficient or mean free path, absorption coefficient, mean free path also. Okay, so these are at microscopic scale, but still small compared to the size of the system. Okay, so in other words, we are going to consider a volume which is macroscopically small, but microscopically large. Okay, so many scatterers, but still a small volume, a dV, a small elementary volume compared to the full system itself. Okay, so we describe the parameter at a small macroscopic scale. Okay, that means that we'll be able to average over many configurations inside the system, but still, this is still elementary, and then we'll be able to integrate over all the system itself. Okay, so at the macroscopic scale, the medium is homogeneous. We can consider like an isotropic homogeneous random system. Okay, so this statistical description. So this again over ensemble.
So
Yes.
it's mesoscopic.
Yes, mesoscopic. Yeah. That's a good term, in between somewhere. Okay. So let's start with absorption. Okay. So we have a volume here. So the medium as we consider like an elementary volume with a surface here dA and a length ds here. Okay. And we have some optical radiation that cross this volume. Okay. And as this radiated power is transmitted through this volume, okay, part of it is lost or gained. Okay, there will be variation of P of omega, so the radiative power. Okay, so if P of omega is the flux of monochromatic radiative power perpendicular to the elementary surface dA along direction u, if ds is the elementary length along the direction of propagation u, okay, which is normal to the elementary surface dA, then the fraction of radiative power dP of omega of absorbed energy along the element of length ds is given by simply dP of omega at s plus ds, okay, is equal to P at S, the dP, so the variation of P, okay, the elementary variation of P as you cross the elementary volume is proportional to P, okay, times the factor mu A here, which is the absorption coefficient, okay. So that's really typical of an exponential decay, okay. You consider that the variation is proportional to the quantity itself. Okay, you lose at each elementary step. You lose as much as the initial quantity. Okay, times the elementary length that you cross. Okay, So if you integrate that, you find actually an exponential decay with an exponential coefficient mu a. So mu a is the absorption coefficient. It's the inverse of light, okay? And actually, as you know, as we learned already, the absorption coefficient is directly related to the absorption mean free path. Okay, one is the inverse of the other. Okay, so LA is 1 mu a. Okay, so easy case, if the medium is dilute, then we can calculate mu a is just the density times the scattering cross section, absorbing scattering cross section of one scatterer. Okay, so you can say that one scatterer times L gives you the absorption coefficient mu a. Okay, so that's an approximation in the case of a dilute sample. Okay, that's what we already discussed in earlier chapters. Okay, so again, so we have this relation here that tells you how much you lose in power as you cross this elementary volume. Okay, by absorption. Okay, now you can say the same thing by scattering. Okay, as the light goes through this elementary volume,
it's constant. It's a constant.
The coefficient itself is constant. The absorption coefficient is a characteristic of the medium itself. Okay. Okay. So yes, this is a constant here. Okay. But the absorption is not constant. As you propagate, you
ask about the absorption coefficient.
So in this simple case, you see that mu a is just n times sigma a, where sigma is the scattering cross section, the absorption cross section. Same thing for the scattering. Okay, as the light propagates through this volume, part of the light will exit in other directions. Okay, so these radiation are lost. Okay, so you can write the same expression dp. So the variation of the power, the radiative power, is proportional to the power itself with a coefficient mu s and a negative sign because it's a loss. It's a loss of power as we propagate through the system. Okay? And this defines another coefficient, which is the scattering coefficient, mu s. Okay, and as you know, mu s is exactly the inverse of the scattering mean free path. So ls is 1 over mu s. Okay. Okay, so the same thing. If it's dilute, you can write mu s as n times sigma s, where sigma s is a scattering cross section for one particle. Okay, so that's again a constant which describes. So again, you see you have here the description at the microscopic scale. Okay, but ls is a more macroscopic quantity. Okay, which actually includes many scatterers. Okay, and tells you how much you lose by scattering when you propagate through the medium. Okay, any question? Okay, and you can group these two effects, so absorption or scattering, into one coefficient, which is called the extinction coefficient. Okay, this is just definition. Okay, so the extinction coefficient is the sum of the scattering coefficient and the absorption coefficient. Okay. Its inverse is the extension mean free path. All that are simply definition, and you recover what we derived last time. If you remember the Beer-Lambert law, okay, if you integrate the expression, you find that P at some distance s is P incident times exponential minus mu times s, the distance that has been traversed by the beam. Okay, so it's an exponential decay, so we lose exponentially the power through the propagation. Okay. An interesting quantity that you may have heard of, or you may sometime meet this quantity, is called the albedo. You know this term? Yeah.
Yeah.
So actually, the albedo tells you what part is due to absorption, what part is due to scattering. Okay. So, for instance, if you look at ink is a strongly absorbing material is black, okay, so it absorbs the visible light, okay. So in that case, the extinction coefficient is mostly the absorption coefficient, essentially. There is some scattering, but mostly this absorption, okay. And here, the case, for instance, of white paint or a cloud, okay, you see the light, the scattering is white, because actually mostly this is due to scattering. There is almost no absorption in this material, okay. So you have actually all the range, and you can define the albedo by this expression here. So A is mu S over mu S plus mu A, okay. So it tells you, so if you see that if you have mostly scattering, no absorption, so you get A equal 1, and if you have mostly absorption, so it goes to 0. Okay, so alpha goes from 0 to 1, covering all the possibilities. So this, you can actually find this type of diagram here, of table, where you have different type of material. Okay, and what is shown is what is the percentage of diffusely reflected sunlight. So the sunlight is strongly reflected by snow, because snow is mostly scattering. Those are different type of clouds, okay, also strongly scattering. As you go down here, actually you get more absorption than scattering, okay. So water, forest, everything which is organic is strongly absorbing, okay. So if you take a picture of the Earth and you plot the albedo of the Earth, actually, you see, so I don't see much here, but I guess the black is 0, so absorption, and the white is scattering, okay. So you see strong absorption in the ocean, and you see here the sound of the desert is strongly reflecting. Also the poles. Okay, this one I'm not sure what I meant here. Total scale albedo. Or maybe that includes also the atmosphere. I'm not sure exactly about this one. Okay, so that's a quantity that you may find new readings. Okay. So, but that's not all. Okay. We see that when the light goes through this elementary volume, part is absorbed, part is scattered. Okay. But there's something else that happened in this story. I call that gain by scattering. Do you have any idea what I mean by that? The previous contribution are negative, okay? That means that we lose power as we cross the medium, okay? But there is a source, actually, something that brings more light, more power into the picture. So what is that? So if you think about the light that is scattered, okay? The scattered light can be scattered many times and actually come back in the direction of propagation. Okay, so multiple scattering actually can contribute positively also to the power transmitted through the system. Okay.
Yeah, like tons of mirror and things like that.
Like what?
Like tons of mirror and things like that.
Yes, it's like many mirrors bringing back the light, but in the direction of propagation. Okay. So it can be a small quantity, but if the scattering is very strong, actually it can be a significant contribution. So during multiple scattering, energy is redistributed in all directions. The energy scattered into direction u prime may diffuse back in direction u. Okay, so you may have light coming back and be diffused in the same direction as the incident direction. Okay, so the phase function, if you remember, P of u prime, is the fraction of the energy flux coming from direction u prime and scattered in direction u. Okay. The increase in the energy flux in direction u between S and S plus S, right, like that, so you can see it better here. So there is a positive contribution to the variation of the relative power here, which is given by the integral over P of the power in direction u prime, okay? That brings actually light scattered in direction u prime back into direction u, okay? So the integral here is over u prime, all scattered direction, okay? And you look at the probability to come back to be rescattered in the incident direction u, okay? So that's the role of this phase function here. This is actually a probability distribution of being scattered from u prime into direction u. Okay, so this term here tells you how much light is bring back by scattering into the direction. It's a positive term. Okay. Remarks. So what do I mean here? If the medium is assumed homogeneous and isotropic at the microscopic scale, in this case, the phase function depends only on the relative angle theta between incident direction u prime and scatter direction u. Okay. So in that case, p of u prime is simply p of cosine theta. Okay. So there is no u prime. You have only one parameter, which is theta. And the phase function can be normalized. Okay. So that's nothing important. And just as a reminder, as we defined that in the previous class, so P of u prime is defined actually from the normalized differential cross-section T sigma over d omega. Okay, well, d omega is the elementary solid angle. Okay, so if you integrate P over all solid angle, you find 4 pi, so the normalization comes from here. And very important parameter, if you remember, G, okay, that's the anisotropic parameter G, that tells you how much you scattered in the forward direction, okay? So this is calculated again from P here. So you integrate UI, so let's see. So UI is the incident direction of the incoming radiation, okay? U is the scattered direction. Theta is the angle between the two. P of u prime is the phase function, so it's the probability density of scattering from ui into u, okay? And the omega is the solid angle, okay? So that's the definition of G. So G actually is the integral of cosine theta times P, the probability distribution of scattering, okay? It's written this way, okay? That's just a notation. The integration of cosine theta. Okay, and G, remember that G is 0 if the scattering is isotropic, and G is close to 1 if you have forward scattering due to large scatterers in general. Isotropic scattering, if the phase function is constant with theta, the scattering is isotropic, so P of cosine theta is 1. An isotropic scattering, 2 examples. First one is the Rayleigh scattering. You remember Rayleigh scattering for small particles? We wrote that that P of cosine theta, so that's actually the scattering diagram, has 2 terms because we have 2 polarization. One was like a circle, okay, and the other one was like 2 lobes like that, you remember? Mm-hmm. And if you consider light which is natural light which is not polarized, so you have actually the 2 components. So that's the phase function in the case of the Rayleigh scattering. And there is another function here which is well known also. It's called the Heinier-Greenstein phase function. Which is given by this equation here, okay? So, and this is all useful for G quite large, close to 1. It is used, for instance, in propagation in biological tissues, okay? It's a heuristic expression, okay? There is no demonstration or whatever. This is given as that, and actually it fits very well the cases of strongly anisotropic scattering. Okay, so different expression. What is nice, this one is related to G, okay, so it depends on G itself. Okay, so that's typical. Okay, so we are done with the different contributions. So we have the contribution, decaying contribution due to absorption, another negative contribution due to scattering, and we have a positive contribution due to the scattering that comes back into the scattering medium. Okay, so that's very simple. Okay, and now with that we can write the balance equation, radiative transfer equation. Okay, that will take into account all these parameters. Okay. So energy balance of radiative energy along direction u. So we consider one direction of propagation u. Okay, we have a volume of the medium here, scattering, absorbing, whatever. Okay. We consider also the elementary cylindrical volume dV. Okay, which is okay. I took 1 for the cross section here, and S for the length of the cylinder. Okay. The wave propagates, let's say, okay, that should be adjusted, but let's say the propagation is at speed c. Okay, so this length ds is c times dt, the elementary time variation. Okay. Okay, so the volume dV contains many scatterers. You can define the density, so that's not very important. So we have two contributions: negative contribution due to the extinction. Okay, so absorption plus scattering along the direction u, and we have a positive contribution to the energy scattered back in the direction u. So let's write that. So I write that in terms of the density power, so the specific intensity of the luminescence, L omega. So the variation of L omega after and before the elementary volume. Okay, so this variation is equal to what? To what we lose by scattering, what we lose by absorption, times L of omega. Okay, so this term is quite fine. Over a distance ds. Okay, plus, so that's the positive part, plus the contribution that is re-emitted from the direction u prime into the incident direction u by this function times L d omega dv. Okay, so we have some incident light here. Part is lost and part is coming back due to the light that is scattered in another direction and back into the incident direction. Okay, that's okay with you? I mean, you have any question on that? Question? So very heuristic. Okay, it's like an energy budget, that power in that case. Okay. So let's see if we want to make more like a differential equation out of that. Okay, to make it like more mathematical. Okay, but the idea is here. So we can write. We can actually make a Taylor expansion of L here as a function of ds and dt. So I write it like that. Ls at s plus ds, t plus dt minus L at s and t. Taylor expansion is differential. How do you say that? How do you call that? Differential derivative of L with s, okay, times the s plus differential derivative of L with time, okay, plus other terms, okay. You can divide by ds, okay. You can divide this expression by ds. Remember in the previous equation there is ds at the end here, so I can divide this by ds and remove the ds here. So if you divide by ds, you get dl over ds here plus dl over dt times dt over ds, okay. Dt over ds, this is 1 over c, okay. This is 1 over c, okay, so we get actually dl over ds plus 1 over c dl over dt here. So we have two terms, okay. The first term can be written like that, so u, the direction of propagation scalar, the gradient of L with respect to R. R is the position, okay, so R is the position, L is the S is the propagation along the volume, okay. And I don't demonstrate that, but I think that's not too complicated. It's just mathematics. Okay, so with that we can write the previous balance expression into a more like differential equation. So we have 1 over c derivative with time of L plus the derivative with S here, which write u nabla of L, okay, equal to two terms. One is due to absorption and scattering, decaying contribution, negative contribution, and a positive contribution due to scattering back into the volume, okay. So we end up with this equation actually, okay. I don't see a difference between that one. Also it's the same. So actually that's the additive transfer equation. Yeah, it's the same. Okay. So that's an equation. So it's an integral differential equation. You have derivative and integral on the other side. Okay. That describe the transport. So that describe actually the transport of specific intensity, the specific intensity of luminance. Okay. And that depends on position, direction, time, and also frequency. Okay. So that's the main equation. That's the master equation to describe scattering in scattering and absorption in dense media. Okay. Very simple derivation. Okay. In a sense, it's quite simple. It's very nice. So if you compare that to the Boltzmann equation for gas, you'll see that it's very similar. You'll see better when we, okay. Say more. There is no analytic solution directly for this equation, okay, but there are specific cases that have been solved. So we have exact solution for specific cases like layered media, isotropic diffusion, okay. So there are some interesting solutions. If not, this can be solved numerically, okay, or with approximate solution. But this is done usually numerically. Okay, so here we have everything we need to address any problem of scattering. Okay, as long as again we can forget about interference effect, we can average over ensemble of different mini configuration. That we want also that the medium be homogeneous, isotropic. With those conditions, we can really address the problem. I'm almost done. You want me to finish, or we make a break? So you always
How
the
much
same.
time does it left? Like,
I have like 8 slides. I have a 10 slides. 15 minutes? 15 minutes is okay?
15?
What? Yeah?
yeah, it's
Okay.
fine.
It's okay? I hope.
Yeah.
Okay. So this equation actually has everything inside. Okay, we have the ballistic component, the diffusive component. Okay, it encompasses all the different regime of propagation. Okay, so let's try to see if we can decompose it into the ballistic contribution and diffusive contribution. Okay, so we consider a collimated beam incident in direction u0 in a scattering medium with volume V. Okay, the incident flux will diminish because of absorption, scattering, and will increase for other reasons. Okay, and we can divide divide it actually into a collimated beam, what we call the ballistic component. Okay, and a diffusive component. So actually, the ballistic is the one that really decreases with distance, with propagation, and the diffusive component is really increasing inside the system. Okay. So let it write it like that. So L, the specific intensity, is as a component which is ballistic only in the direction u0. That's the delta here. Okay. That's the component, ballistic component, and the diffusive component LD, okay, in all other directions. Okay, so what we can do actually, we can insert this decomposition into the radiative transfer equation. Okay, and by doing that, we'll get two equations: one for the ballistic, one for the diffusive. So if I do that for the ballistic, so I just reproduce the equation on the top here, the radiative transfer equation. So you just replace the ballistic component, and you have this simple equation, okay, 1 over C P over dt of L plus the term which corresponds to the derivative with the distance, okay, is actually reduced by this amount, okay, due to scattering and absorption, okay, and you see that the last term here, the fourth, this term here, is not part of the equation for the ballistic, okay, because this is light that has been scattered and injected back in the same direction, okay. This is not ballistic light; it's diffuse light, but in the right direction, okay. So this term is not part of the ballistic, okay. So we need to keep it for the diffusive. Don't forget it in the next slide, okay. So that's, you recover here the Beer-Lambert law, okay, the exponential decay due to the scattering and absorption. Okay, so that will be reduced as it propagates through the medium. That's the ballistic. Now the diffuse intensity, okay, so I call that the increasing part, okay, because, okay. So it satisfies this equation. So the same here, you just replace here L omega by this component, the diffusive component. So we can have this term is the same. This term is there also, okay. The diffusive component has also some loss due to scattering and absorption, okay. And the term that corresponds to the part that is reinjected, the diffusive light that is reinjected in the right direction, the incident direction, and we have to add this term here, which is the ballistic part, which is also scattered back into the direction of incidence. Okay, so we have a new term here. Okay, we cannot ignore that term for the diffusive component. Okay, so this is the source term generated by a redistribution of the ballistic component into the diffusive component. Okay, so when all the energy is carried by the diffuse component, okay, when we lost all the ballistic photons, the ballistic light, okay, then actually we are in a regime where the radiative transfer equation simplifies, okay, and it simplifies into an equation which is called the diffusion equation, okay. And that will be actually the subject of our next chapter, okay? So when we can ignore the ballistic component, we'll be in the regime of diffusion, okay? And this is exactly the same equation as the diffusion for heat, okay? Diffusion equation, same as diffusion equation for heat and for photons. Okay. So what I want to show you to finish here today is to show you that you remember the transport mean free path. Transport mean free path is related to this small g that tells you that you have propagation, you have scattering in forward direction, okay, anisotropic scattering. So the transport mean free path actually comes naturally from the radiative transfer equation, and that's what I want to show you here. So I start again from the radiative transfer equation here, okay. I multiply each term by u, the vector u, okay, which is the direction of incidence, okay, and I integrate all the expression over 4 pi steradian over all solid angle in all directions, okay. So the first term here, second term here, okay. On the other side we have this term here, which gives you that, okay, with the integral. We have, and the last term there, which is given here. So here I just permitted the integral. You have integral over d omega L. In L there is no u, okay, so you can take it separately and integrate only p u times p over, oh sorry, yes, over u. Okay, and this is integral over u prime. Okay. So this term is still in the integral, but this term L can get out of this part. Okay. So here you recognize here a quantity that we defined before, which is the radiative flux vector. Okay. So this is the Q that I defined before. Q is integral over all direction of L times u times d omega. So it's here, it appears here, it appears here also, okay. Remember that this integral u times p is 4 pi g u prime, so g, the anisotropic coefficient, okay. So this term is here, you recognize it here. So here we have g. So I can, so look, so if you look, so what I'm doing is so this term, I don't know what to do with that, so I put it on the other side, on the right side, okay. This term I put it on the left side, so this is this derivative with time plus mu s plus mu a times q, okay. So this is q 1 over c d over dt q plus mu s plus mu a q, okay, plus this term, okay, so this term, so that will be a minus here, minus mu s, so there is another mu s contribution times g, this is exactly g, okay, times again q, okay, so you see that you have mu s, you have on the other side it will be 1 minus g. Okay, so actually you get exactly the two terms here. You see? So the derivative with time for q, okay, plus this time it's not anymore mu s, but it's mu s times 1 over g. So what is this quantity here? 1 over this quantity, this is exactly the transport mean free path, okay? Plus mu a, that's the absorption coefficient, times q is equal to this term over there. Okay, so you see that naturally, actually, you have to consider not mu s, not the scattering mean free path, but you have to introduce the transport mean free path. Okay, and that's a transport equation. Okay, so we are at a larger scale. What is important? What is important is not how much of the ballistic is lost, that's the scattering mean free path, but what is important is after how many scattering events I'm losing the direction of incidence. Okay, so if the scattering is very strongly forward, okay, it will take many steps before you lose that direction of emission. Okay, so that's really the quantity to consider when you consider transport equation. Okay. So this state regime. So if you eliminate if you don't consider the time, then you get the expression for Q. Okay, which is 1 minus 1 over. Okay, so that we don't need. Okay, so actually, so I define here the transport mean free path. So it's called L star in general. Okay, so L star is 1 over mu s times 1 over minus g. Okay, or in other words, Ls over 1 minus g. So you see that S star is equal to Ls if g is equal to 0, isotropic scattering. And if g is close to 1, then it can be much larger than Ls. Okay? So this new length scale is implicit in the radiative transfer equation. It can be very different from the scattering mean free path, Ls, if scattering is anisotropic, if g is much larger than 1. Okay, and that's typical in the case of biological tissues. Okay, in that case, you see, I mean, you have many types of scatterers with different sizes. Okay, you have all scales here, but the large scatterers they promote scattering in the forward direction. Okay, so that's why G is quite big. It can be up to 0.95. Okay, so Ls is about 100 microns. But LT is about 1 millimeter. Okay, so it's important if you want to do imaging. It's not Ls that you have to consider. It's LT. Okay, which is good. That means that actually you can keep track of the source over 1 millimeter. Okay, after 1 millimeter you lose the source. Okay, so if you for instance you can use like fluorescent markers that you can inject in the body, okay, and okay, if you are below 1 millimeter, you can actually see that source, and you can image the tissues. But beyond 1 millimeter, it's already gone. Okay. So, any question? So I wanted really to show you. I mean, it's quite relatively simple. Actually, the presentation is really heuristic, and it's really with hands. Okay. And once you define these quantities, which are semi or macroscopic or mesoscopic quantities, okay, then you can really define this equation, which is really the beauty of the transport approach. And with that, you can solve many problems. Okay, this is used in many fields, and relatively simple to address. Either you can solve it in simple cases, or you can solve it numerically. Okay, so we'll go next time we will consider only the diffuse part, the equation related to diffusion. Okay, the diffusion equation, and we'll see actually that. There are different ways to solve it, and it's even more tractable than the radiative transfer equation, and very useful in many cases. Okay, so with that I'm done. If you have any question.
Thank you.
Okay. So it's probably more tractable, more convenient than the theory that we developed last time. Okay. But it's just neglect completely the interference effect. Okay, so that's the limit. Okay, but most of the time you don't mind about that, and doesn't really play a role. Okay, and then the light actually is described as like particles in collision with other particles. So thank you. If you have any question, if you want to discuss anything. I will try to prepare a list of papers so you can start. Now we start to have some material, it will be better to wait for the end, but then you need some time to prepare, okay? So there are papers related to localization, to coherent backscattering that will come later. But
maybe before the next lecture, you can upload the presentation to the Lambda, and so you could maybe
before
prepare.
I wanted to do it. I just didn't have a minute to do that.
So we could prepare for the lecture.
Yeah, right. So it's there. I was about to put it. Well, last week I put it.
Yes.
I do it now.
Bye, Shabbat.
Bye. תודה רבה.
Bye. See you next week.
Actually, I used to work in a lab here in Geograph, in the earth sensors.
Yes.
Yeah, and when you showed the albedo, it was familiar because this is what I did in my research. Yeah. But I tried to apply the network theory to the albedo. Yeah. And take a different startup cumulus regions and try to find like interconnected networks, try to formulate it mathematically. And I looked specifically at the albedo and the outgoing flux. So I did the analysis on this data from the NASA satellites. So it was nice to see that. But it wasn't enough because I didn't have all the physics behind it. And now I see.
Now you understand better.
Yeah, I understand it better.
That it's related to the work of Shlomo Gil.
Yeah. Yes. So now I wanted to understand more the physics side, so I wanted to show.
We are working with you.
Yeah.
We have collaboration.
What kind of collaboration?
We explore network of lasers.
Wow.
Actually, we can reproduce this theory just with the coupled lasers. We can see this transition, this rapid transition.
The phase transition there.
Yeah.
About
we see that in the lasers. It's very nice. And very simple actually. It's a very simple experiment.
Yeah.
Right. So,
that's interesting. Oh, it's interesting. I mean, it appears everywhere. This
it's
about.
amazing. It's just amazing. So there is like a race between different labs working with different type of materials and trying to demonstrate this theory.
Yeah, everybody is doing this now. So I wanted to go like and learn about the core of the things, you know. Like it was, I needed to know the physics behind it. I couldn't just stick to one
right. So
subject.
But that was the idea of Shlomo. He wanted to go from mathematical concept. You wanted to go to physics, back to physics, and demonstrate that in physical system.
Very interesting. Do you have any papers?
So there is a paper which is submitted, which is under review. I can send you the link to the archive.
Yeah.
By the way, I have to check here some news. It's already I think August 18. It's August 18 and it's still under review.
Yeah, it takes a lot of time.
No, actually, before Sukkot, we received the 2 reviews, excellent reviews. I said, okay, it's good, it will go through. And then I don't know what happened. I think the editor received another review, which maybe was not that positive. I don't know. Then he sent the paper to other people. I mean, it's like.
Where do you publish it?
To PRM, physical regulator.
Oh yeah, in the physical.
It's a good paper. No news since we are waiting for the last review of it.
Yeah.
So submitted on August 18th. Can you imagine that?
Maybe you try and contact them.
No, I contacted them already. They say we have to wait. No way.
Yeah.
So,
Shlomo is working with everybody.
no, yes, we put everyone in the.
I don't think there is a single group or professor here that is not working with Shlomo. Not even in the physics department. In the sciences.
Okay.
So, thank you. Yeah, it will be very interesting to read about the research.
Yeah, so let me, it's not sure. Do we have your email? What's your email?
It's Amit, A-M-I-T, dot K-M-O-R.
K-M?
K-M. K-M. Yeah. At gmail.com. Yeah. Thank you.
I can send you the paper. I send it to you.
Oh yeah, thanks. I'm just thinking, I remember when I was working on the research, I had a problem that, it was a personal problem, that the data, I thought it was not, like the resolution was not good enough, in my opinion, yeah? But the professor said that, no, it's all right, 1 kilometer and 1 kilometer, even 5 and 5, 7 and 7, I don't know. Something, it's divided up to grids, yeah? You have the grid. And I thought, I don't know, maybe, would there be a better way to, like...
So what is the system exactly? What is the physical system?
It's, you take you have a few satellites, a constellation of satellites, different kinds that take, the images from above. So you have different types of sensors. There's a LiDAR and basically, what do you mean by physical system?
No, so what is the network? Network of what?
Of stratocumulus regions. It's like the regions where storms are formed. Like you take a place, like a specific geographical coordinates, like a box on the Earth, like North Atlantic and Southeast Pacific and a few of these regions. And then you create this kind of time series, you know, and you want to check correlations between these places where the storms are created, but in different times of the year. So you want to see if there is some kind of interconnection between them. And you look at different kinds of parameters, specifically the albedo. This is what I was looking at. Yeah. So I thought, yeah.
How is that related to this transition? Usually you have like two networks that are coupled together.
Yeah.
In Schumann system approach, it's a network of networks, interconnected networks.
Yeah.
So in your case, what is the interconnection? What are the two networks?
Yes. So I'm not exactly sure yet. I mean, this is what we were trying to formulate. We were trying to kind of understand how to apply it. And I did not reach that point yet. But then I left that research because I wanted to understand more about the networks themselves.
That was a long time ago, or you are still working on it?
It was just like a month ago. I switched.
Yeah. You switched to another group?
Yeah, I went to Shlomo.
Now you are with Shlomo.
Yeah, I was with Tom Goren from the Earth Sciences department.
And over there, they were not doing networks.
No, that they are working with Shlomo. That is the project. Yeah.
Okay.
It's the.
So you are still with
the climate. Yeah.
I see.
It's very interesting, the calculation.
So in our case, we don't have networks. There is actually it's only one laser,
yeah,
which is it's coupled with itself. It's self-coupled.
Wow. Okay.
So you take the energy and the intensity and you couple it back to the laser.
Wow.
And that's enough to see the good transition and all the physics, the plateau, all these phenomena.
The plateau, yeah. Shlomo wants to prove it for the quantum with the super conductors.
So yes, that's the work with Aviad.
Yeah. With Aviad. Okay. Thank you.
Okay, bye.
Bye bye.
See you next week.
See you next week.
So can you send me that presentation?
What do you mean presentation?
Yeah, this presentation.
Ah yes, sorry, I forgot that you don't receive them.
It's fine. Like the last week I received from Kaiwi.
Okay.
This week I
So I
received.
can send it to you.
Professor, regarding that FTTD simulation, I wanted to ask what to do next. So now I'm running the simulation.
Okay.
I'm at the end of taking the Fourier transform and getting. I got some spectra which I was discussing with Reno. So I wanted to know how we can go
So
next.
you have to tell me what you are able to do, what you can do. You show me, and from there we are going to start this project on coupling laser.
Okay.
Random lasers. Oh, that's nice. Yeah, let's start that. Should go forward. 6 PDF version. That was okay, it was clear.
Yes, yes, today, yeah, it was like, okay. But I didn't, yeah, I had this one doubt when you said about gain. When you mentioned about gain, the question I had was, suppose we have a source which say it emits 100 photons into this scattering media, and the light scatters in all the other direction and comes back into the same incident direction. But again, the total is 100 photons itself. How do we call it as a gain?
The gain in the direction of
Yes.
where you are looking at. You are looking in a given direction.
Yes.
So there is part which is gain because it's a positive contribution.
But earlier also we had input only the 100 photons, right? So first, suppose let us say we have input 100 photons in U direction. So the photons go into the scattering medium, they get scattered everywhere and come back to the
Some of them
yeah,
can
some
come
of
back.
them. So even when they are coming, the end output we have the intensity lower. Or even if we recover everything, we have the same intensity.
Yeah, for sure it would be lower, but there is a contribution which is positive.
So you're trading in terms from the reference point of this direction, we are getting some other input inside the scattering medium. So
which is really unexpected. I mean, we think that everything is lost because of absorption and scattering, but no, you have a correction, and this correction actually, maybe I didn't say it, but this correction exactly this is exactly the G that comes in the 1 minus G term.
Yeah, I was looking from the perspective of outside the scattering medium. So I was looking from the perspective of outside scattering medium. I was thinking, how do we have a gain when there is this many things? But when we go into the scattering medium, yeah, we can see the.
No, but you can also put real gain in this.
Putting real gain, that is
you can
entirely
put a
different.
positive mu. That's possible.
That is entirely with respect to this.
Or 6. It's not too big. Okay, I wanted to check my programs. So I can answer them. If I can find them. I see if it's fast, otherwise I will take more time. Let's see how we define all these quantities. Variance. And we have Copilot in MATLAB. It's good. It's
The licensed version of MATLAB. The licensed version you use. The version that you have MATLAB.
yes.
The licensed.
Yeah, yes. New version. You have access?
No, but I use from the lab systems
Yeah.
through Jokings.
But any computer that is connected to the wall, I mean, you can.
Yes, but again we have to input the email ID.
Right.
So, using Jokings. And I've been logged out of the system for now. I'm not able to access through my username.
You have been logged out.
Yeah, logged out of the office.
Which system?
I think from the entire.
So you had an address. You had a VIU
No,
address.
not VIU address, but I had a username using which I could access the system alone.
Which system would you use?
Any workstation or any other computer system in the lab.
So today you are disconnected today?
No, I think for past 1 week or something.
Really?
Yeah, I was using Leonid's.
So we should ask.
Oren?
Well,
So today even.
and we should ask him to. You have to be 1 year to be able to have VIU.
I don't know about that regarding. I think so. So this is the program.
So that's a program, for instance, cross correlation. What do I mean by cross correlation? Compute ensemble correlation. This is in space, not in frequency. So, for instance, I have here. I see I tried different type of normalization. So either I take the field divided by the square root of the variance, or I take V minus average over average, or V minus average over square root of the test. So I have to check which one I chose it here. It's not, I wanted to see the frequency correlation as well.
There is one get frequency name file.
No, that's so one program is calling the other, so I have to check. Let's see if actually that problem. It's a very long time ago to remember what I was doing. Let's see. Average. So I can close this one. Specific cross correlation. Average. The ensemble average. Okay. Over configuration. And this vector over frequency average. So you see I have a vector which is implicit function. This is just the number of values that I took. That's the number, sample number. Start and the realization, start realization. So that's just divided by that. So this is just an average. Okay. that's easy. Let's look at variance. Check these two columns per n. So here the variance, I take VV minus average times the conjugate. It's normal, that's the radio definition for variance. So I take, you see, I take for the field, I take VV minus AV divided by AV, average. So V minus average or average. What I took here. And my correlation is just, so it's a sum, okay, but GG is the spacing of mix. I take the average of V, so this V here, okay, this term here. So that's the, I guess, all the frequencies from 1 to, yeah. No, yeah, this is the mean, which the mean is over configuration.
Mean is over the entire the frequency range for a given delta.
Or maybe over the number of realization, I'm not sure.
Yes, this average. So you have
Of
this,
realization, right?
and this average is the mean.
So that's the same. This exactly. Oh, but this is EI?
Yeah, that's I. Yeah. Here I have for E, but again E minus average.
So you have to check what is V here. Correlation. Who's the frequency of the confidence and the correlation function VV. Omega divided from the opposite omega. Besides it, okay. Average over and stuff. So this is average over configuration. No, over frequency and over configuration. Please check which function is analyzed. VV or VV divided over.
Different ways.
Yeah, you see, it's a question. What do you use for to properly? Where is this super N? So I read the file and I concatenate those files. Yeah, this is just a technical problem with the instrument. I mean, it's just to make the file. So
now it seems that I'm using the average. So this value GG here, this is the number of configuration, and then I divide it by ER because it's plus 1. What is n total? N star plus 1. So what is ER precisely? For instance, I don't see the intensity correlation. The intensity correlation. Set the desired variables, study the statistics. Field, intensity, so my D is defined here. Drop phase, you can define V as you want, because the idea was okay, okay, field. All those are different ways to define V. Intensity, the V is just V times the okay, so if I go to correlation here, my VV takes, so if it's intensity, I take intensity and I use average intensity, over intensity, divided by, I just want to check these two here, variance, variance. So, what are variance here? I'm not using this one. Using the average only, average.
this particular quantity. Okay, correction is I take this quantity and I apply the correction. Okay, so any function, let's say intensity would be intensity minus average intensity over average intensity.
We first do that average and then we take the correlation.
And then on this quantity I take the correction. Is that what you're doing?
No, yeah, kind of same, but there is no divide by average. That I do after I consider the correlation function.
Oh, but that's okay because this is this over this times this over this. The square.
Yes.
So you have 12. So it's the same. Right?
So that means there is yeah, I did this extra that when we discussed last time. There was I minus I mean in the denominator. That was extra, which is not there. So yeah, if I eliminate this, I'm getting the good result. So I will go with this. And for the field correlation, I took the average first for E field for 100 configurations, and then I do this part. And again, for this, while averaging, this I is the intensity, which I'm taking in the denominator. Like again, E into E star.
Yeah, I agree with that. I don't see how my program works in that case.
For E field was the confusion that we had.
Because here, if it's the field, I'm taking the this is just V. Okay, there's the complex field that is measured by the instrument. And I'm taking what is the average? The field. What is the average of the field? It's a complex number. I sum the field. That's what configuration.
There is SR and ER. SR is equal to total number of elements, right? R.
Realization. No, ER is not defined. I don't know why. Okay.
Okay.
That's for intensity, that's for E. So if it's for E, I take VV over square root of the variance. Square root of the variance, that's what you want.
No, that I
For the field. Still it's the same, right?
variance is when we get this one, right? For del mu is equal to 0.
No, not for intensity, for the field. The variance for the field will be E minus E average.
Okay, variance, yeah. Square root of variance.
Actually, the average of E, I think the average of E is 0 because the field is just oscillating. So the average is 0. How do I put it? So don't put the average here, VV over square root of variance. variance is when you take the square. V square minus E squared. I think it's the same. E squared average.
So it is something like this. Square root of variance is
Variance is VV minus average and conjugate. So it's VV minus average. So it's VV minus average minus square average. Okay? That's your intensity. There is no, I think the average is 0. I don't see anything about the average for the field, but I guess it's...
No, but this average is with respect to the different configurations. So that doesn't come zero.
Really?
Yeah, but because for each new, I have an electric field for different configurations. I take the entire average of that.
Well, it is
Here
sure.
for 100 configurations.
If you have an infinity of configuration, then it should average to 0. No? The field averages to 0. No? The field is just oscillating plus minus. Well, it's a complex number, right? But on average, it should be. Yeah. Field average is 0. Okay. Intensity average is 0. So I think it's correct. That's what I did. I did the same.
Okay, so then I can go with this expression.
Just understand the variance here, calculate the variance, I'm taking this expression here, minus average. But for the field, this is meaningless, I guess.
This you are using for intensity, you have mod square. So this particular average you are using is only for intensity. But for field, I think it's something else different.
No, but for the field, I'm using VV over square root of variance, if it's correct, okay? But square root of variance is here, and variance uses the equation, and also we said it is minus 1. Use FCDN with for no, but I think this is correct actually.
Yeah, then I can work with this.
After that, you can look in papers, also like the happened in papers.